Okay, new chapter, chapter 18. So, a couple terms we've got to cover here. You got to know these terms. A population is a group of individuals of the same species in the same area. We kind of talked about some of these, I think, the first day of class, what a population and an ecosystem was. We talked about those, but in this area, for example, in the immediate area is a population of humans. A species, now if you get into biology more, what makes up a species, that's a moving target of sorts. For now, we're just going to say it's a group of organisms and about the same area, capable of interbreeding. So if you're of the same species, you can interbreed. Third point's kind of important. Okay, individuals don't evolve. Populations do. Okay, it's not like X-Men. It's not like a comic book thing where an individual evolves. No, in biology, individuals do not evolve. It's populations evolve over time. It's a fairly important slide. But where does evolution start? Evolution does start at the individual level. Okay, because that's where all evolution is a sum total of mutations that somehow proliferate in a population. Okay, so it's going to start at the individual level, but evolution occurs over time to a population. And then the final point about the sexual reproduction, the point there is that people that have good alleles or have some type of mutation that helps them sustain themselves in an environment, they tend to reproduce. Therefore, sexual reproduction helps to spread those alleles through a population, which kind of makes sense. If you can somehow survive better in an environment, you tend to reproduce more. Okay, are you good with that? Okay. So variation in a population. Traits tend to vary in a population. Okay, all people in a population have a series of common traits, but there's variation in those traits. Pretty simple ideas, noses are different sizes, eyes are slightly different sizes. There's always going to be variation in the traits, but there are a common set of traits in any population. That makes sense, doesn't it? Right. A little more something. But the next slide is a lot more important than this. I consider this as walking around knowledge. This is the important stuff. A gene pool and allele frequencies. So gene pool is just a collection of all the alleles open to a population. But think of the gene pool as, a gene pool doesn't say is an allele more present or less present. It just says it's just the total collection of them. You go to like blood type alleles, right? O is a very common allele. If I looked at if I described the gene pool of humans, I'd say there's 3 alleles. There's an A, a B, and an O. I wouldn't say anything about the number of them. I'd just say there's 3 alleles in the gene pool. But the other idea is allele frequency. Allele frequency is the number of alleles for each characteristic. So in that situation, I'd say the allele frequency of an O allele is higher than A or B type blood alleles. And all the pictures trying to show you this whole thing is a gene pool, right? And from the gene pool, alleles are pulled out, if you will, to make organisms. The different proportions of alleles in it, some alleles are more present than others. That's the allele frequency. Next, are we good with this? Good. Okay. Next one, mutations. We talked about this before, and we'll talk about it again. Is mutations are the ultimate source of new alleles in a population. Mutations are the ultimate source for new alleles. So mutation happens, that's a source of a new allele. Most of the time, the vast majority of the time, a mutation that happens, the result will have no effect, or it will not proliferate. It will not remain in the population. But sometimes a mutation happens in the right situation and the right environment, and that mutation, it continues in the population. But the environment decides if a mutation is good or not. Okay, in some environments, a mutation may be good. In other environments, that same mutation may be bad. We talked about an example of that last time. We were talking about sickle cell trait, right? And that gives you an immunity against malaria. Kind of remember this a little bit? Okay, well, that's a good example. In some situations, some environments where there might not be a lot of malaria, that trait would be bad, be deleterious, would not persist. In other environments where there is a lot of malaria, Plasmodium species, then you would have, that trait would be an advantage, and then it would persist. Okay, 3 types of mutations, I won't name them, I'll just let you write those down. But again, all of those mutations, it depends on the environment. If the environment selects for that mutation, then it's a beneficial mutation. If the environment selects against that mutation, then it is a net lethal or a negative type mutation. I think, just someone mentioned about extra credit. I'm not going to give you points, but I might have a quiz after this. So in case I forget, remind me, and I'll remind you about a quiz, and I'll make a quiz up real fast. So just remind me. Just remind me, because not a lot of people came, and I'd rather I don't want you to say, hey, here's some points. I'll make a little short quiz up. Just remind me at the end. I'm sure someone will remind me, right? All right. Okay. Okay, new topic is genetic equilibrium. Let me go back. Were you guys good with this, or did you come? I'm sorry? Okay. Bless you. Okay, genetic equilibrium, and I don't want to get, sometimes I'm up here just showing slides, and I don't want you to lose sight of what we're really talking about. We're talking about changes in populations over time, or you can call that evolution. So all of these somehow come back to that idea of genetic changes in populations. So I don't, sometimes it's that the theme is lost with all these slides, so I don't want you to lose sight of the theme. Okay. So genetic equilibrium is this theoretical idea where population does not change over time. If a population is in genetic equilibrium, over time, it is not evolving. It is not changing on a genetic level. But you see the word theoretical? Okay, it's at least in biology, it's like a perpetual motion machine. Okay, it's a theoretical device. Right, but here, this is a theoretical situation. We don't see genetic equilibrium happen. Now, we see situations where it's really close to genetic equilibrium, but there's always going to be some type of change that will lead to evolution. But what we do, and how we look at it as biology, is we'll look at how close a population is to genetic equilibrium, and that tells us something about that population. If it's really close, then it's not evolving. If it's further from genetic equilibrium, then it's evolving at a much faster rate. So what 4 processes? Why can't we have genetic equilibrium, or a perfect situation of genetic equilibrium? One is mutation. Okay. Where are we going to see mutation? Mutation can happen during DNA replication. DNA polymerase, no matter how good it gets, okay, it's still going to have mutation as it replicates DNA. Okay, the error rate for our DNA polymerase 3 in humans is, I think, 1 out of 100 million base incorporations. There's going to be an error. But still, there's still an error. So there's always going to be mutation when you replicate DNA. Very, 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 very small percent, but still, it will still be an error rate. So we cannot get away from that idea of mutation. When you have DNA replication, statistically, you have to have some type of mutation in there, even very small amounts. Natural selection. We talked about that before. Right? When you have a good allele and a bad allele, the environment selects for the good allele or selects against the bad allele. Okay, so you're always going to have some type of selection where some alleles are favored, others are disfavored, just based on what they do. Bless you. Another thing that kind of precludes genetic equilibrium is genetic drift. What, the whole thing? Genetic drift is just a change in allele frequency over time. So, for example, let me give you a good example. Genetic drift. Let's just say in a population, that's a good example, it's genetic drift, real fast. Let's say in this population 10,000 years ago, okay, we have 75% had O alleles, 25% had A alleles, and let's say 20% had A, and then 5% had B alleles. And we let time progress the way it does, and right now, O is 30% O alleles, 40% B alleles, and 30% A alleles. Does that make sense? Kind of over time, the proportions of the alleles have changed. Okay, or maybe said another way. This, see how so we have 75% O, 20% A, and 5% B. That's allele frequency. 10,000 years ago. This is allele frequency today. Genetic drift is the change in allele frequency from sometime in the past to another time. That work? Gene flow is the entry or the exit of alleles. Just use this diagram. Just read some numbers here on this. Okay, let me just read you this diagram. A good example here. Gene flow. Let's say there's 4 alleles. A, B, O, and Z allele 10,000 years ago. Okay, and for whatever reason, 10% of the population had this Z allele. But for whatever reason, it was not favored in the environment. It was not selected for, and all people with that allele died off. What would happen? That would be gene flow, in which an allele completely leaves the gene pool. When that allele leaves the gene pool, that would be gene flow. Okay, or an exit of an allele. Alternatively, alleles can actually enter into the gene pool. That's also gene flow. So alleles leaving or entering is gene flow. Okay, but what's the whole point with this? That all of these things are happening. So we can never get genetic equilibrium. We never see a situation where you have 10,000 years ago, 75% O, 10% A, 5% B, and 10% Z, and then now the same thing. There's always going to be a shift in the allele frequency in a population. If there is no change in this allele frequency, that would be genetic equilibrium. But that's a theoretical situation. We don't see that happening. Okay. 5 conditions needed for a stable gene pool. We got to know these. And again, this goes back to the idea of genetic equilibrium, that all of these do not happen. Okay, none of these are going to happen in equal amounts. These will be really close with some of these, but still, we're always going to find a population that is not 100% on these conditions. Okay, so the first thing is mutations do not occur, right? But we've said, yes, mutations do occur. Sometimes they can be induced by chemicals, sometimes they can just happen during DNA replication, but we know that mutations do occur. Okay. Populations are infinitely large, but there's no such thing as infinite, right? So there has to be some number there, and the smaller the population, the less genetic equilibrium you have. No gene flow, meaning no alleles are leaving or entering the gene pool. But again, that happens, right? We have a mutation, we have a new allele come in. We have natural selection against an allele, we have alleles leave. So there has to be gene flow. Random mating, what does that mean? Well, that means you just mate with anyone. But what's the whole idea of mating? The whole idea of mating, okay, is that you want to select a mate who has the best alleles. So you look at a mate and say, I think you have the best alleles, and then you mate, and then those alleles go on to the next generation. But if there's random mating, you're not selecting. Let's see. If you have random mating, does that allow for natural selection? Not as much, because you're not selecting for the positive alleles. Bless you. So if you're randomly mating, good alleles are not rewarded, bad alleles are not punished. Yes. Oh God, I love that movie. Brando. Yeah, if you've not seen the movie, it's actually a very good movie to watch. Idiocracy. Idiocracy. Okay. And then finally, all individuals survive and reproduce equally. And again, we don't if all individuals survived and reproduced equally, you would not favor good alleles. You would not disfavor bad alleles. Okay. Now we have an equation, and you're going to see this if you continue in biology. You want to probably circle this because you'll see this a lot more. It's called the Hardy-Weinberg Formula or the Hardy-Weinberg Principle. Hardy-Weinberg. I know, it's a big one, isn't it? Okay, and the P and Q here refers to the proportions of alleles. Now this is for a 2-allele system, but you can have it for a 3-allele system, 4-allele, no matter what. But the more alleles you have for a particular gene, the longer the Hardy-Weinberg equation is. It's not bad. It's not bad. It's not bad at all. I'm not going to give you an equation on the test, but it's not bad. It's not a bad equation. Just what we use Hardy-Weinberg for. No. What we use Hardy-Weinberg for. Let's show you what we use it for. And this is I'm not going to give you a Hardy-Weinberg equation. I just want to show you, when you see it done, I think it makes a lot more sense. And it looks like a big monster of an equation, but it's really not. It's really not. So Hardy-Weinberg. So we have 2 alleles. Let's call A. How about that is purple. And little a. How about white? Not work. White flowers, purple flowers. Okay. How many alleles do we have for this one gene? 2, right? What we're looking at is flower color. We have 2 alleles. Okay, so Hardy-Weinberg would say what? If we have, in a population, if we have 30% with the A allele and 70% with the little a allele. Good so far? Okay, so P2 P2 is the amount of homozygotes. Let me see if I can. That's right. Okay. 30%, 70%. T squared is 0. Let me say, okay, 30% as a decimal is what? 0.3? And what 70% is a decimal? 0.7? Okay. So 0.3 times 0.3 plus 2 times 0.3 times 0.7 plus Q is 0.7. That would be a Hardy-Weinberg equation. Okay, but we'll just get past that part. Okay. Okay. Natural selection. Just know that what Hardy-Weinberg equations are used for. You don't need to work on an equation on the test. Okay, so natural selection patterns. Okay, so what's natural selection? You're doing what? You're choosing a particular allele, or you're choosing against another allele. It turns out that we have 3 models that we can choose an allele or choose against an allele. Directional, stabilizing, and disruptive. And it looks a lot harder than it is, trust me. When you see these pictures, it makes a lot of sense when you see it. Okay, we're going to have slides for directional, stabilizing, and disruptive. So save some room for it. Okay, directional selection is when one extreme is selected over the other. Okay, so with traits, we have a natural variation in traits. What the book uses is different colored butterflies. One's white, one's purple, or one's darker. With directional stabilization, one of those alleles is selected against, or one of the other alleles is selected for. Either way, over time, what happens? So if you go at the top, we have some white, some intermediate, and then some dark purple. But for whatever reason, the dark purple ones are selected for. Therefore, over time, the dark purple allele is more predominant than the white allele. I'm sorry? Another good example people have always, when I did this class, the example was if you were tall versus short, and for whatever reason, tall people somehow had an advantage. Over time, what would happen? The proportion of tall people would increase because the proportions of shorter people would have decreased. So that's directional selection. Okay. Again, directional selection, we have 2 extremes. At the end, we have extremes, and in the middle, we have a mean. And with directional selection, one extreme is favored for, or one extreme is favored against. And over time, the side favored for will become a greater proportion of the alleles and of the population. What could be an example of this? The book mentions a moth. What happened was there's whiter moths, there's darker moths, and because of pollution in an area, soot got over the trees. Okay, if the trees went to a darker color, what would be favored? What would be more favored in that situation? Darker moths or lighter moths? Darker moths. Okay, so there was a directional selection, and the darker moths had an advantage, and they were selected for, and the lighter moths had a disadvantage, and they were selected against. Okay. Another example is resistance in bacteria, antibiotic resistance. Okay, bacteria occasionally will get resistances to antibiotics. It's rare, but since there's so many bacteria, it happens. But what happens is, over time, the bacteria that have that resistance to antibiotics, they proliferate because there's a selective force in hospitals because of antibiotics, and the ones that do not have that resistance, they die off. Okay, so basically all this is you're selecting for an extreme, or you're selecting against another extreme. Okay. Stabilizing selection. Stabilizing selection is not the opposite, but it's more selecting for the average at the cost of the extremes. I'm sorry? You're selecting for the most common phenotype. So you're not relating it to heights. You're not selecting for people that are really short or very tall. You're selecting for the average height or the average of some feature. And over, I'm sorry?
Are you saying like if the soot wasn't on the tree, then the one that's colored like the tree already
would have the advantage, yes. But with this is not an example of that, but the previous one, yes. Because, well, the last one, that actually happened in England during the past 50 years, is the trees were a lighter color, and the moths would, there's a variation in the moth coloration, and because of coal-burning plants or, factories, the trees became darker. And the darker moths, which were rarer before, had an advantage because they were not seen on the darker trees. And then that phenotype was selected for. And then the normal moths became more apparent on the trees, and that was selected against. Okay, that's stabilizing selection. And then finally, there is disruptive selection. Disruptive selection is you're favoring the extremes and you're disfavoring the average. So think of disruptive as almost the opposite of stabilizing. And because of disruptive, you tend to get two polar extremes in a population. Okay. Did you make it? Are you good at that? I'll give it another 30 seconds. Okay. And again, just the pictures of natural selection. You're selecting for. When I say, what am I saying when I say selecting for? What does that really mean? Exactly. You guys hear what I said? When I say selecting for, I mean that those are being allowed to live and reproduce. If I select for something, that means they are, if I'm selecting for these, this means that in future generations, these will reproduce more. If I select against something, what does that mean? They're going to die or they're not allowed to reproduce. And if you can't reproduce, do you pass those alleles on? Nope. So let's just say selecting, I select for these guys and I select for these guys. These reproduce, and either these die or don't reproduce. In biology, not reproducing is essentially equal to death. A couple generations later, since these guys reproduced, surprise, surprise, we see more of those alleles because they were able to pass those to future generations. Because we prevented these from breeding or decreased their ability to, we see that that allele frequency is less. And then give it a couple more generations, and we see that those extremes are now selected for. Okay, so that's when I say selected for, these were allowed to reproduce and pass alleles to future generations. These were not. Okay. Yes?
So basically, with direction, only one extreme.
Only one extreme is selected for. Correct.
Stabilizing
It's the average is selected for. The extremes are selected against. Is the extremes are selected for. Maybe, yes. If I did put them on the test, they would be those exact charts. I would never put something like from Google Images up and say, go with it. I would always use things from the PowerPoints. Most likely, yes. It depends. I might just show you, what I might show you is something like this without the red arrows, this, and then this, and then say, what is that? Okay. Example of disruptive selection is, this is just an example of it from the book, is the length of the bill, is that both extremes are selected for. Some have a more narrower one and one have a wider one. But that's just an actual example of disruptive selection. Okay. Okay, balanced phenotypes. Our balanced polymorphism is where two allele types or two or more alleles are kept at about the same amounts, or both are kept at high numbers. One example is sickle cell anemia. That's one. Another one, I mentioned this in my other class, but not in here. Color blindness. Does anyone even know why color blindness? It sounds like a really bad thing, doesn't it? Who wants to be colorblind, right? Doesn't sound like a very good thing to have, is it? But you know what? Here's the thing. Is there any advantage to being colorblind? There is? Actually, there is. There is. Do you know where you're going to find a large proportion of colorblind individuals? Or let me say this. Do you know where you're going to find a lot of individuals who are very adept and a skill that are colorblind? Graphics. Like graphics. No. Huh? Not China. No, I'm talking about a profession. I'm talking about a profession. I'm sure you find a lot of people colorblind in China, but they got 1.2 billion people, though. But yeah, I'm sure you find a lot. No, but what? Anyone kind of know what I'm alluding to? Snipers, army snipers or military snipers. People that are colorblind can see through camouflage a lot easier than people that are not colorblind. And see how that could be an advantage if you're a male hunting and you could see an animal in the brush that you could not see if you had normal color vision. That would be an advantage, wouldn't it? It would definitely be an advantage. So even now, we see you look at who's a good sniper versus who's not a good sniper, and there's actually been statistics done on this. People that are really good snipers in the military tend to be colorblind. There's a positive correlation. It's not to say the best are colorblind. You have to be colorblind to be a sniper, but you have an easier time of seeing through camouflage if you have color blindness. So, at some point, thousands of years ago, think of males out hunting. They could see some animal in the brush that a normal vision male could not see, and that gave them what? An advantage. And because they had that advantage, think they could have passed that allele on. Yeah, because what we call it? What was that term we defined that as? Passing that allele on. You were what? Selected far. So that allele was selected far because the people that had it could get game easier, could get food easier. They could get food easier. They could reproduce easier. Okay. Another example, though, is sickle cell anemia. If you have, there's two sickle cell types. There's sickle cell disease and there's sickle cell trait. If you have both sickle cell alleles, you have the disease. You don't have protection from malaria in that situation. But if you have one of the alleles, remember we've said that everyone has two alleles for a gene, right? If you have, here's that picture we've been going over, right? One from mommy, one from daddy. If you have the sickle cell anemia allele here and then a normal one here, okay, that's sickle cell trait. If you have sickle cell trait, you have a protection against malaria. Okay, so again, another example of that. Yes?
My dad has that, and I would carry it for him, I don't know.
Does he have sickle cell, full-blown sickle cell, or sickle cell trait? I'm going to guess, just statistically, he probably has an allele for it, but not both alleles. Because if you had both alleles, you die relatively young if you have both alleles. He's probably a carrier, in which case you would have a 50% chance of also being a carrier. So you are a carrier? Okay. Then you would have what's loosely called sickle cell trait. So if you have, here's your two chromosomes, one from your father, you have a sickle cell allele, and then the other from your mother, you have most likely a normal allele. So there's disadvantages to it, but there are advantages to it, though, if you're ever in a place with high malaria rates, because you have a protection against it. Yes. You have a protection against getting malaria. Sickle cell trait. People with sickle cell trait, they have a harder time getting malaria.
Why is that?
Because the plasmodium, which is what causes malaria, enters into the red blood cell to survive. And people with sickle cell trait have a slightly different red blood cell shape. Because what happens in low oxygen environments, the cell becomes more crescent shaped. So, okay. Okay, genetic drift. And this is the last thing, and then we'll have that really quick quiz. So genetic drift. What's genetic drift? That's the change in allele frequencies over time. Let's not worry. You can write that fixation down. You might see that, but I'm just going to talk about genetic drift for a minute here. Okay, over time, there is a change in alleles in a population. Okay. Some alleles come in, some alleles, the frequencies are going to change. And that's just based on environment. So think of it, while you're writing that down, let me just draw a real quick example here. Okay, so this is genetic drift. 20,000 years ago, for this allele, for example, 20% had this big A, 80% had the recessive version. Now, the dominant version is more common, the recessive version is less common. That's genetic drift. Okay. The frequency of that allele and the gene pool has changed. Okay, so what do we have to know about this? Genetic drift happens more in small populations than in large populations. And that's actually an incredibly important thing. Because what happens, and actually, believe it or not, we're also, all of us have a stake in this. A little bit of a history lesson here. All of us, everyone here, no exceptions, all of us come from, and we know this based on genetics, that we think about 80,000, 60,000 years ago, about 10,000 years ago, most of what we consider humans died off. And there was just a very small group, one last little island of humans left. And from that island of humans, all of us came from. And we can do this by genetic studies. But the problem is that we had a very small population, so we had actually some genetic drift and genetic bottleneck even with our species. So why is that important? Because with small populations, you have more of a genetic drift. Here's 10 individuals, and here's 100 individuals. So you can have a lot of genetic drift in a small population. So because our species actually had a genetic bottleneck, there was some genetic drift in our species. So we can actually see this in the genetic history. We can look at people's genetics and trace it back and actually show that we have had actually a lot of genetic drift in our species. Okay, this is also a problem if you try to reintroduce species to an environment. We've heard all these organisms that are nearly extinct, right? Heard that, and then we bring them back from extinction. Well, the problem is, if we had a small population we brought back from the brink of extinction, there's been a lot of genetic drift. They've lost a lot of genetic variability because of that. Okay, last slide here, and then we'll make that short quiz while you write that down. A genetic bottleneck, and again, that goes back to that example I said about humans, is what? It's a drastic reduction in the number of individuals. Because if you have a genetic bottleneck, what happens? Think of that gene pool, right? That gene pool goes from being something the size of a swimming pool to something the size of a little kiddie pool that you get at Walmart for $20. You know what I'm talking about? Those little blue pools that are like $20 and they're the lamest thing. Well, that's a genetic bottleneck. Okay, the gene pool has really, really reduced in size. But the problem with that is what? When you get past that bottleneck, you're going to lose a lot of alleles in the process. Really good example about humans, our species, human beings, or Homo sapiens, sapiens. We are really we can actually trace back a genetic bottleneck for even our species. So I'll bring it. I'll look up the numbers on that. I don't remember the exact number that we think it is off the top of my head, but I'll make sure I tell you next time. Okay.